When I was first learning logarithms, none of it was very intuitive. And so I was thinking about why, and I think the first thing that occurred to me is that exponents aren't always intuitive. They grow really fast, way faster than multiplication. And we can see this in an example. If we start out with one rabbit, we want to multiply that by 5. Multiplication is just repeated addition. We're just going to paste this 3 times, and it's 1, 2, 3. It's very intuitive. We get to 15. And if we're going to go one more than that, it's also very intuitive that that's just 5 more rabbits. It gets us to 20. But now if we want to sort of look at rabbits doubling, that's when it's going to start growing really fast and becoming way less intuitive. And we're going to double it to 4. And we're going to select them all. We're going to double it to 8. And we're going to double it to 16. And this number is going to get really big, really fast. And we got all of a sudden we're up to 256 rabbits. But how many times did I just double that? Well, maybe I forgot. So then I can look at 256, and I can take the log of that. 250, log 2, right, is the base. We're doubling things. And you can see that I just doubled that 8 times. So this is an example to get some intuition into the exponential growth. Another good example to look at to gain some intuition is the powers of 10, and the number itself is the sum of those powers of 10. But then you could ask, what comes in between these columns? What if you had a column for 0.5 and 1.5? A fractional power is actually finding a root of a number, so a half is finding the square root of a number, and the square root of 10 is 3.16, etc. And you can jump over and try some raising 10 to these powers, and you'll see that 10 to the 0.5 is going to give you the square root of 10, and the 1.5 is going to be 10 times the square root of 10. 2.5 is 100, and so on. And so if you look at this and you kind of review your log identities, it's a great thing to do just to sort of see how they connect to this, and it'll give you a really good intuition. But to make it more intuitive, where if we're going to count by 5s, we can kind of get a really good sense of like what a number is. Like we can't tell what this is, but we can see that this is 10, 20, 30, 43. But as the numbers get bigger, it's going to take, it takes a lot longer, start counting these numbers. So this sort of intuitive repeated addition type of growth is useful, but it's also very slow once the numbers become very big. And so then we can look at this exponential growth. And so here we have, let's think of this as a number line, but also a radius. You can imagine a big circle around this. And we have a rabbit here, and below him is the number that shows the distance from the center. And so we can think of then, so it's like this funny way to think of logarithm is we're going to locate the rabbit. Maybe the rabbit is named George. We're going to locate George. And so if we click locate, we can see now that the counting by the logarithm goes much faster than counting by the exponent is much faster than that linear growth we saw where we were counting by 5. If this is the 207th rabbit, another way we can think of the logarithm is the generation. So if the rabbits are doubling, and then this 2 to the cube, 2 cubed is 8, and then here we have 16, 32, 64, 128, 256. So between 128, the 7th generation, and 256, the 8th generation, then we're going to have some of these fractional positions. And so then one interesting thing to note about this within these generations is that, say you're between the 6th and 7th generation, if you're halfway at like say 96, you see we're at 65850. But so now if we're halfway on this one, let's say at like about 192, this is 75850. And so each of these are proportional in their range here, which is another interesting thing to explore and then play around with and make the connection to the log identities. And then so just to go really big here, let's just make this a really big number, and then And again, if we were going to locate the rabbit way out here, just see how much faster that is to count than just counting by fives when you count by the powers here. Okay, so if we jump over then and take one final look at how we graph the log, we'll find lots of things to explore to gain some intuition. So looking at what we have here, we have a base that we can change between 2 and 10, and then we're going to graph the log of that base. And this equation is the log identity. We're scaling the natural log by 1 over the natural log of our base to give us the log in that base. And so this is the log base 2. And if we look at the exponential, you can see the exponential grows very quickly and the log grows slowly. And if we increase the base, the exponential grows even more quickly and the log grows even more slowly, which is intuitive. And turning off the exponential for now, we can look at some of the interesting boundary values. So for, say, x equals 0, the log is undefined. And between x equals 0 and x equals 1, all the values are negative. Let me change this to blue. And this is because, right, what do you have to raise 2 to get a half? We have to raise it to -1. 2 to the -1 is 1 over 2, 1 half. And so it's the case with all the numbers that are fractional. You have to have a negative exponent. And then at 1 itself, it's 0, because 2 to 0 is 1. And it doesn't matter what your base is, because any number raised to the 0 power is going to be 1. And then the other interesting value to look at is the value at the base itself. And at the base itself, what do you have to raise 2 to get 2? You have to raise it to 1. And this also applies to whatever the base is. So if the base is 3, to get back 3, you have to raise 3 to the 1. And the same for 4, and so on. Then going back to 2, and now recall the example with our rabbit friend George, and we made the fun mnemonic locate George as what log is, or locate the generation, and we were looking at the halfway point between generations. So let's just look at the halfway point, which is what a new one, x equals 3, and we'll make that red. And we see that we see this value 1.58496. And then if we were to look at the next generation between, say, 4 and 8, and the halfway point being 6, we see that it's proportional to 2.58496. And then between the next one, just to really belabor this point, 8 and 16, halfway between 12, you see the same proportion, 3.58496. That 58496 appears again. And then again, I encourage you to look at the log identities and to see why this is so. And then going back to our original example with 10, remember we were asking what was between the columns we were using for numbers at the power of 10, where we had 10 to the 1 is 10, 10 to the 2 is 100, and what you were asking what happens in between 1.5. And so what we can see here then is that, well, let's start with the 0.5, and we can see that this is the square root of 10. We're landing at x 3.1628 is the square root of 10, and its log is a half, the square root. And then 1.5, well, when we jump all the way out here, we see the square root of 100, 31.62278. And then, right, 2.5, square root of 1,000, 300, And this really gives you the intuition of how slowly this is growing. Where was our... There it is. 3.16227. One final example to look at is powers of 2. So just as before we had columns of powers of 10 to represent a decimal number, here we have powers of 2 to represent a binary number. And in the same way, each column as a power of 2 is added up to get the final number, which in this case is 15 in decimal. And so the interesting application of this is that if you have a number and you want to know how many bits it takes to represent that number, you can take the logarithm base 2, you floor it, and you add 1, and that'll give you the number of bits you need. So, for example, the number 15, log 2 is 3.9, etc. Floor is 3 plus 1 is 4, and as we can see here, we can represent it with 4 bits. So hopefully these examples help give some intuition around logarithms. Thanks for listening.